I looked on the wall, at the old clock on the wall. By that time, it was 10:30 then. I looked down the bar at the bartender. Said, what do you want now?
Sure.
You want brother? One scotch? One beer? Well, my baby, she's gone. She ain't gone tonight. I ain't seen my baby since I was a whole life. I want to get drunk till I'm off of my mind. One brother, one scotch, one beer. And I sat there, getting high, stoned, knocked out. By that time, I looked on the wall at the old clock again. And by that time, it was 1:45. Last call for alcohol. I said, hey, Mr. Bartender, what do you want? One burger.
What was it I needed? I guess that's it. Okay. Oh, well. There we go. I don't know where to zoom in. There it is. Okay. That's going. I guess we'll just share screen. Okay, let's see. Okay, welcome all. Good to finally see y'all in person. Still only seeing about half of you though. Everyone's in bank robber mode, and I just want to comment real quick that that very significantly affects my ability to learn names. It just does. This was what I experienced anyway in the fall. It took me about half the semester to learn. I think it was about halfway through that I finally learned everybody's names. So please bear with me on that, and apologies. Of course, you know, we've been going already for a couple of weeks, so all of our course preliminaries are out of the way. It's just I just wanted to say a quick hello. Now, while we're here, I guess I'll point out on the lecture schedule that don't forget we have a second homework assignment, right, due day after tomorrow on Gradescope. So I hope everybody's making progress on that. Of course, we finished section 1.6. last Friday, I guess it was, right? So hopefully you've had the weekend to get a lot of that done, if not all of it already. And then there's just a question of what we're going to finish today, which should be 1.7. I expect it'll be 1.7 only, but with that, I have to wait until the end of today to decide for sure. Okay, so let's dive right back in. Here's what we were doing. Oh, I guess I should also say, point of etiquette. Since we're not in the Zoom thing anymore, we no longer have this problem of me not being able to see raised hands. So if you have a question, which I encourage, of course, you know, I'll remind you, I have a whole write-up about asking questions on the Sakai site. Go ahead and raise your hand at this point because I can see it at this point. Okay. Okay, so last time we were talking about cylindrical coordinates. It's pretty much polar coordinates, recall, right? It's polar coordinates in the XY plane, and then for a given point, you project down, and then for the third coordinate, you just use the z, same z as we use in rectangular coordinates. So pretty straightforward formulas, right? All this is the same as in polar coordinates. And side note, yes, z is still z. We talked about a couple of easy examples, not hard to persuade yourself that's a cylinder. Pretty easy substitution of this formula into here to persuade you that this is a sphere in cylindrical coordinates. Okay. And then where things did get a little bit weird with this last example, so that is a cone, and doesn't seem like it's doing enough work. It's just, I mean, what a simple little equation, right? But I mean, in some sense, what allows this to be such a simple equation for a, well, not so simple surface is that cylindrical coordinates is really set up really well to describe something like that. And of course, now the way that we can conclude that this is a cone is to realize that no matter what value of theta you pick, any value of theta, right? That's the same equation, independent of the theta. So any changing of theta that you might do can't affect the equation. So you always get the same cross sections in all of these theta planes. And that means that it has to be a rotation around the z-axis. Welcome all, good to see you, come on in. So being a rotation, of course, all we have to do is look at, in some sense, any slice of it. And don't forget the fact that, of course, r can be negative, right? So we're not gonna make the arbitrary choice to require r to be positive. So z equals kr looks like that, right? You take that and rotate it around the z-axis, and you get a cone. Okay, let me pause there. We did all this last time, so it's just a kind of a quick review. Since it's been 5 days, I figured maybe go ahead and review that real quick. Okay, everybody's happy? Okay, all right. So being as it is pretty much polar coordinates, and we spend a bunch of time on polar coordinates, cylindrical doesn't usually get a lot of time in class. So in fact, I'm going to just move on already now to, oh, you know what though? Quick little warning. Yeah, it's a good thing I had this written down. Don't overuse R too casually. When, oh, I've got something I need to be a radius of something. Let me just call it R. Whoa, slow down. R is it's a variable now. So it's a coordinate. Right. And so if you have a sphere, okay, that's nice and all, but if you're going to be using cylindrical coordinates, this is not acceptable to be used as the radius of that sphere because it's busy, right? It's busy being a coordinate. So just be careful and make sure you don't confuse your variables. Okay. All right. So spherical coordinates, also very often referred to as polar coordinates in 3 space, just like cylindrical coordinates is. However, in this case, not a good idea. This is really very significantly different from polar coordinates. Cylindrical coordinates, it's pretty much polar coordinates. Spherical coordinates, different. So please don't make that choice. I think it's misleading and it will make it hard for you to get the right pictures in your mind. So here's how it works. You have a plane of space, right? Well, there is a unique half plane hinged on the z-axis that contains that point, right? Okay, so that defines theta, and of course that's the usual theta. It's the same theta from polar coordinates, conveniently, and that's where the similarity ends. Okay, so with that defined, there is then an angle measured off of the positive part of the z-axis. So from the positive part of the z-axis toward the theta half plane. So the direction that is the positive direction is defined by whichever direction theta points. Okay? And that angle phi then defines a direction, in that theta half plane. Therefore, it defines in fact, an actual direction in space from the origin. Okay, so we've got theta defines a plane, phi combined with theta defines a direction. And then, well, with that direction defined, then there's just a question of, well, how far do you go in that direction? And that how far you go leads you then to your location. That's what, that's how spherical coordinates defines a point. Okay, so let's pause on this real quick. Is everybody okay with this? Everybody see how this works? Very important to notice, rho, this variable rho, not the same as r. It's not the distance to the projection down to the xy plane. No. It's the distance, right, to the point. Well, oh, look what I did. I said distance. Let me be more careful. Distance, of course, is an intrinsically positive thing. Rho is a coordinate, does not have to be. Rho is how far, right? Or pick your wording, but put it in quotes to emphasize that it's not necessarily positive. Okay, so I'll point out that a couple of these, you have to think about what happens if they're negative. What happens if phi is negative? Well, we have this idea of what the positive direction is. Positive direction is toward the theta angle. So, well, what happens if theta is, if phi is negative? Well, if phi is negative, then you're talking about back that way. That's what happens when phi is negative. And then likewise, what happens? Whoopsie, didn't mean to do that. What happens if rho is negative? Right? If rho is negative, well, instead of going that way, you just go same direction, just backwards. In other words, you go exactly the opposite direction. So pretty sensible, pretty much what you would expect, I think. All right, pausing again for questions. Everybody good? Yes, please. Oh gosh, that depends on who you ask. I'm going to use this as a kind of a typical, right? But you don't really have to. Yeah, it depends on in some textbooks, in some physicists tend to like to, for example, switch phi and theta. In fact, they literally, this thing here they call phi, and this thing here they call theta. And having done a double major in math and physics, this drove me batty, right? It's like, wait, which class am I doing here? Okay, which one's the theta? Which one's, drive you crazy. So yeah, the ordering down here is, I'm going to say it's conventional for this class, but be prepared for who knows what in the real world. Great question. Anybody else? How do you connect these to rectangular coordinates? There is a really good way to think about this. I think this is my favorite way to think about it. And that is to, let's focus on this triangle right there that I'm going to redraw, looking at it kind of, if you will, sort of straight on, just to make it a little bit easier to see. So that triangle, notice that angle phi, you can see it right there. And then of course, little geometry tells us it's also that angle right there. And I've got a right triangle then. Let me use orange, it's a little bit easier to see. I've got a right triangle where I know one of the angles and all the edges. Right, and I forgot to label here, but this height here, of course, is Z. So some real easy trig, nothing to it. Right, high school trig for R and Z in terms of spherical coordinates. And in fact, this one little observation of simple trig on an easily seen triangle in that picture actually tells you everything you need to know, because specifically R being known, then I can just reuse what I already knew, namely X is R cosine theta and Y is R sine theta. That's a recycle. I don't have to derive that again, it's clear. And then, of course, Z is already one of those equations, no additional work required. So I think this is a really beautiful way to think about it. And in fact, with the armed with this idea in my mind, these formulas right here, I have actually never memorized, in my life. And I've used a ton of spherical coordinates. I never can remember every single time that I use spherical coordinates. I have to think it through. Okay, wait a second. So, and I've got this exact triangle in my mind. And I think, okay, so R is the, okay, I see how it goes. And then I remember X is R cosine theta, Y is R sine theta. Boom. So now what you do in Math 219, up to you as to whether, probably the best choice, honestly, would be to do both. Go ahead and memorize these formulas and remember the picture, because if and when you at some point in your life, 100% you're going to forget, right? But if you remember how to derive where they came from, then you can forget all you want and just rederive. So anyway, I suggest maybe doing both, but up to you. Everybody good? Okay, a couple of examples. An easy one. Let's see here. Did I write down? No. Okay. Well, so not hard to persuade yourself that rho squared is equal to. I just have it written down right there. Rho squared is x squared plus y squared plus z squared. Right? Easy Pythagorean observation. And with that in mind, very easy to persuade yourself that that equation is a sphere. And again, thus the name. That's why they call this spherical coordinates. Constant values of one of the coordinates give you spheres. So, all right. Now here's a hard example. It's about visualizing all the different ways to understand a point in spherical coordinates. And you remember how we were talking about polar coordinates are not unique? Well, neither are spherical. No surprise. But there was two ways to write a point in polar coordinates in some sense, right? There was the one where R was positive, and then there's the one where you make a half turn and then R is negative. Okay. Well, that's because there's one angle. That one angle gives you two options as to, well, which way do you go? Well, there's two angles in spherical coordinates, and that means that there are four ways to write a point in spherical coordinates. And I think it's a good little mathematical weightlifting, let's build some muscles, right? Let's get practice thinking in spherical coordinates to think through what are those four ways to represent, let's say, for example, this point in spherical coordinates. Now, it's really easy to, you draw the picture and you note these coordinates, and then you, draw these various triangles and et cetera, and you can persuade yourself without too much trouble that this angle is pi over 3 and that angle is pi over 4. Real easy trig. Make sure you can do that, of course, but that's not hard. So with that in mind, though, how would I describe this point in spherical coordinates? So first, let's start with the easy one, the obvious one. Everyone's favorite choice here would be to say, look, that point is clearly in that plane for which theta is pi over 3. Now, okay, so if theta is pi over 3, what does that mean? A lot of people would tell you that means, okay, well, that means that phi has to be pi over 4. And certainly that's one of the options, right? If you have theta and phi as drawn here, then no sweat. Then you just have rho be this distance here, positive, because we're going in the correct direction, and everybody's happy. But remember, there's two different ways you can do each angle, right? So in fact, an alternative way to think about this exact same point would be to think of phi as being negative. Let's see, I need blue. So keep in mind, there's where phi is 0. There's the positive direction. So what if I did negative? Let's see, let me try to make that straighter. What if I did negative 3 pi over 4? That defines a direction which is exactly the wrong direction, which means that if I then use a negative rho, it gets me back to the same point. So that's an alternative spherical coordinates for the same point. Everybody see what happened there? So you've got a negative, this is the negative 3 pi over 4 phi angle. That sets me up to use a negative rho. Okay. Now that's 2 of our 4 options. The other option, correction, the other pair of options says instead of using pi over 3, like I had done previously, let's say, no, let's go around an extra half turn in the theta direction. Right, let me do better with that plane here. There we go. So I can have that as my theta. And with that as my theta, well, okay, so here's where phi is equal to 0. There's the positive direction for phi. So I could have a negative pi over 4 as my phi. Gets me going the correct direction. Rho is positive. Or I could do a positive 3 pi over 4, because keep in mind, this is the positive direction now because of the way theta is pointing. Positive 3 pi over 4 for the phi angle, and then a negative rho. So it's weird, right? It's a crazy little exercise. There are lots of ways to make spherical coordinates. And I think, again, it's a good little mathematical weightlifting, make your spherical coordinate three-dimensional visualization muscles a little stronger. So I like to go through it for that reason. This is also a really good one for y'all to look at afterwards, after class, and think through and try to persuade yourself, maybe try to draw some of these pictures yourself. That's good practice. Drawing pictures is hard. And is a very useful skill in a class like this. It's so heavily geometric, right? So all of that's good practice. Pausing again. How we doing? All right. Okay. So here's a nice little application. I think this is interesting. I don't think this is in the book, if I remember correctly. I just like to make the observation that the spherical angles actually relate pretty strongly to longitude and latitude on the surface there. They're not exactly the same, but they're pretty closely connected. So here's, here's the Earth, let's say, and I'm going to make the prime meridian there is going to be in the direction of the positive part of the x-axis, right? Just, and by the North Pole up there, South Pole down here. So sort of the most convenient way that we can represent the Earth on here. And with that observation, notice that theta it's just east longitude. It's measuring how far, kind of around, this way around the Earth is the meridian that you're on. How about that? Right? And then notice that phi, now it's not equal to north latitude. But they're closely connected. Phi and north latitude always have to add up to pi over 2. So weird, but there it is. So that gives us then, if you have spherical, and of course the radius, the rho is always the radius of the Earth. Every point on the surface of the Earth is that far from the center of the Earth. So that means that if we've got spherical coordinates, we can conclude longitude and latitude, and vice versa. Okay, so what's the point to this? Why would anyone care? It actually gives us a strategy for computing the answer to a really hard question, an otherwise hard question, I'll say. And that is, given 2 locations on the planet, you're going to take an airplane from one to the other. How much jet fuel are you going to use? Right? Really important question. What path should you take, and how far is that shortest path? Hugely important question. So, well, golly, it looks like a really hard problem. I mean, this curve is it's a sort of a weird curve. I mean, depending on where those points are, you might actually have to kind of go over the North Pole almost, that kind of thing, right? So how do I figure out that distance? And the answer is surprisingly easy. What you do is you observe that if well, I'll do it like this. If you know the longitude and latitude, well, then you know the spherical coordinates. If you know the spherical coordinates, well, then you know the rectangular coordinates. So I can actually, pretty easily, and thank you, spherical coordinates, right? But I can write those 2 locations not as, longitude and latitude. I can write them as vectors and rectangular coordinates. And once you know vectors and rectangular coordinates, it is super easy to dot them. And of course, we know a bunch of stuff about dot products, and among other things, it relates directly to the angle between the vectors, and that angle between the vectors relates very conveniently to distance, that distance that we wanted. So it just happens to be that there's a nice little sort of connect the dots argument that moves through some Math 219 ideas, Math 218 ideas, that gives us the answer to, again, what would otherwise be seemingly a very hard problem. Everybody on board? Now, there's a bunch of details that I skipped, so, exactly what is that connection exact? I mean, we've got that written down, but you got to actually do that. Yeah. Okay. All righty. Okay, so moving along. Just like with polar coordinates, it's not that hard to convert equations, depending on which way you're going and depending on the circumstance. But easy example, this is we know that this is a sphere. This is a sphere that's kind of centered, if you will, at 1 on the x-axis, and then has radius of, square root of 1, namely 1. How would I describe this in spherical coordinates? Just like we did in polar, it's very helpful if you kind of expand out the algebra first. Once you've expanded that out, you can notice stuff like that. And then, of course, that. And we're basically done, right? I mean, so just plugging in the conversion equations gets you into spherical coordinates, and then a little easy simplification, and this is how we would actually write it. Okay. How we doing? Everybody happy? Okay. All righty. Okay, so this book has a discussion about what they call the standard basis vectors for these new coordinate systems. Oh yeah, please.
For the last one,
Yeah.
why isn't it rows squared when you simplify it?
Oh, well, yeah, so first thing I did is I canceled one of the rows with one of these rows
Okay,
and then
gotcha.
subtract. Yeah. No, sure. Yeah, good. Anybody else? Okay. Yeah, so standard basis vectors. Now I know y'all have seen, you may have seen them as IJK, you may have seen them as E1, E2, E3, same thing. I like this notation better because, you know, not everything you do in math or any of its many applications is restricted to 3 dimensions. Right? We talked about that before. I mean, easy examples in economics, you can have endless numbers of variables running around all in the same equations and systems. And it's nice to have the flexibility to be more than 3-dimensional. So I like this notation. Anyway, why are these vectors important? And reminder, standard basis vectors is the term. Various reasons. This is what I think is actually the most important reasons, is that they connect, sorry, circled the wrong thing. They connect very, very valuably to linear combinations, right? If you have a vector's coordinates, you can write that vector as a combination of the standard basis vectors, and the coordinates themselves are the coefficients. It's a really nice fact. If you want to try to do something like that in the other coordinates, in spherical coordinates, polar coordinates, what have you, yeah, it just doesn't work very well, and so that does not translate over. But these vectors do have other features. They're unit vectors. They are pointing in the direction of a single coordinate increasing and the others being constant, and that's something we can reproduce in other coordinate systems. And so the book gives explicit formulas for all of those. I'm going to go through and just talk about how to think about those, what they call standard basis vectors in these different coordinate systems. And if you want to expand these out and memorize them, I suppose you could. I wouldn't particularly encourage it. I think here, certainly it's much harder to memorize the equations that I'm about to show you because, well, it's just a lot. But what is, I think, again, easier to understand how to get them than what those results are. So let's start with this point here. And we're doing polar coordinates, 2 dimensions, of course. And what is the unit vector pointing in the direction of r increasing? Well, you can just see this vector. It's clearly parallel to that vector, which has got coordinates x comma y, and so it's just pretty easy pitch. Here, let me color code that. This vector is x comma y, and the green vector that we're looking for points in the same direction, but has magnitude 1. So look at that. Let me raise that up. You can see better. Is everybody happy with that? So again, don't memorize the formula. Understand the reason. The reason will stay in your mind much longer. Okay. Okay, now how do we get this formula E theta? Hard to directly connect it to the vector r there, but easy to see, however, that it's just a rotation, 90-degree counterclockwise rotation of that. So just rotate, right? That's a Math 218 thing. There's a matrix that does rotations, and negative y comma x instead, right? So there you go. So now again, if you want to memorize, you can. I never have. Those occasions when I've needed them, I just think it through like I'm showing you here. Cylindrical coordinates, of course, is polar coordinates in 3 dimensions. And so, well, pretty much, I mean, there is a, third, comma 0, third coordinate there. But otherwise, those equations are certainly motivated in exactly the same way. But there is the third coordinate And EZ, of course, is, well, it's always pointing straight up. So it's our familiar E3. Okay. Now where it gets fun is spherical coordinates. We start off with that vector being, of course, in the same direction as the position vector itself. And so again, you divide by the magnitude, same, morally the same concept that we saw with the R, the ER. The theta is actually exactly the same as the E theta from cylindrical, which is exactly the same as the E theta from polar. So that's an easy sort of, that's just a recopy. I don't even really have to do anything there. And where it is actually a little tricky is how do I get my hands on that vector? How do you, gosh, I guess I could say that I'm going to rotate it. I'm going to rotate that vector, 90 degrees, but I'm rotating it in a different direction depending on what theta is. And that's, so that would be kind of a hard way to think about it. The easy way to come up with this is to realize that it's just a cross product of that and that. So handy. Okay. All right. So my advice is that you understand the ideas that lead to these formulas like this, understand these little geometric tricks that we talked about, and don't actually memorize the formulas. I certainly never have. Yes.
So when you have these, so like the unit vectors equal to like
Yeah.
the coordinates over a row or like coordinates over R, what exactly does that mean? Like,
What does this mean?
yeah.
Oh yeah. Okay. Yeah. So this is a vector, right? And I'm multiplying that vector by a scalar. The scalar is 1 over rho.
Okay.
Yeah. So vector scalar division is just like vector scalar multiplication. It's just, dividing. Yeah.
Okay. So just that is just the vector.
The coordinates of this vector are x over rho, y over rho, and z over rho.
Okay.
Is that what you were looking for?
I think so.
Okay. Yep. Good. Anybody else? Yes.
How do we get E theta per cylindrical?
Yeah, it's pretty much exactly the same as that.
So where did that one come from?
So this one came from noticing that in polar coordinates, it is just a turn. It's a it's a counterclockwise 90 degrees turn from that vector. Yeah, and so if you remember from linear algebra, if you want to rotate something counterclockwise by 90 degrees, there's a rotation matrix. So I'm just applying that rotation matrix to that ER vector. Yeah. Does that sound familiar? Do you remember rotation matrices? Maybe not? Okay. Show of hands. I'm just curious. How many people remember rotation? Okay. Well, maybe we've uncovered something I should talk about. So let me talk about that a little bit. I'll find a little space right here. Okay. So if you have XY plane, and if you have a vector here, and if you want to rotate, you get a vector there, you want to rotate 90 degrees. All right, what we're going to do is we're going to identify what this matrix is by understanding its columns. Now, how do I understand columns of a matrix? Columns are images of the standard basis vectors. So what I really need to know is what happens when I rotate E1 90 degrees. And then what happens when I rotate E2 to get the second column? What happens when I rotate E2? And so the geometry argument I would make here is that E1 rotates into E2, right? And then E2 rotates into negative E1. And so this right here is the matrix that rotates vectors in the plane counterclockwise my colors An inconsistency with the colors there. This is the matrix that rotates counterclockwise 90 degrees. Everybody good?
So in the standard basis vector for theta, it's just pointing in the, like, is it parallel? Is the point that it's in parallel to the XY plane?
In cylindrical coordinates? Yeah, absolutely. Yep.
So you drew it kind of going up.
Well-
That's a two-dimensional.
Well, yeah, that's right. Well, here I'm in the XY plane,
Right.
right? And so the XY plane here is it's down here like this. So, from this point, ER, let's see here, ER would be kind of like that, right? And then E theta would be, just 90 degrees turn from that thing, but also horizontal, all horizontal. Is that cool? Yeah. Okay. Good. Okay, let's see here then. Yeah, so nice formulas. Do keep in mind, again, I already kind of previewed the disappointment here, but these standard basis vectors are not as good as rectangular standard basis vectors. For one thing, rectangular standard basis vectors are constants. These are very conspicuously formulas, right? Not constants. So that's annoying. They do not work with linear combinations the way that rectangular coordinates do. So let me remind you, this is, one of the huge this fundamental huge fact about linear combinations is that any vector, its coordinates tell you how to find it as a linear combination of standard basis vectors, right? Huge fact about linear combinations in linear algebra. And that doesn't work anymore, right? So if you have the spherical coordinates, right, you cannot just make those the coefficients, right, in a linear combination of the spherical standard basis vectors. Oh, absolutely not. Just doesn't work. So that's unfortunate. Yes.
Can we talk about or see an example of when we would want to use this?
Want to use the standard basis vectors? When is this going to come up? I think they're probably going to use it. This is my first time teaching this course and the first time teaching the subject out of this book. So there's a lot of firsts here. I'm not sure what they plan to do with it. My best guess is that they plan to use this when we get around to doing what's called change of variables, which is a technique for triple integrals or double and triple integrals. So yeah, I mean, there's going to be a time when this will be useful, and maybe they have other plans as well. I'm not sure, but that's not something I can really show you right now.
Okay.
So yet, very often, the applications of things that we cover come after we build up a lot of stuff. We need a lot of extra tools to be able to do the next big application. So this is one of those usually the case, frankly, kind of examples. Yeah. Okay. All righty. Oh yeah. So quick side note: the standard basis vectors, unfortunate choice of words, are orthogonal, and these happen to be two. That's a coincidence. Lucky break. There is no rule that says a coordinate system's standard basis vectors have to be orthogonal. We just get lucky here. Okay. All right. So that finishes chapter 1 for us, and we move now to chapter 2. Reminder: all of these notes, of course, are on the section Sakai site. The one for my sections in the resources section, and so this file. Chapter 2 lecture notes, or whatever I called it, is there. Okay, so we're going to start off talking about functions. There's some definitions that have to get made, lingo that has to be noted, that we're going to just need to use here and there throughout the rest of the course. So first of all, let me make sure everybody's clear what a function is. Honestly, this very often gets swept under the rug or treated sloppily. And it here and there causes problems. So I want to emphasize, this is a really important point about what a function is. A function is not just a formula. A lot of people think a function is a formula. That's part of what a function is. A function really is a trio of three things, and it's that trio together. All of these three things are part of the definition of what a function is. It's a domain, which is where the things come from that you put into the function. I like to call it a target. The book uses codomain, whatever term. Target is just more relatable to me. It's a less scary looking word, and it's one less syllable. So, all right. So the target is, okay, these things that went into the function, when they come out of the function, where do they land in? Okay. And then the formula, what the book calls a rule of assignment. And so in other words, given an input, given an input, I need to have exactly one output defined. That's what this rule of assignment does. It tells me for any given input, what is my exactly one output. Okay, so the domain for this function here is that. The target codomain, if you prefer, is that. And I'm defining here the natural log function. And so the rule of assignment is, well, whatever real number between 0 and infinity you give me as the input, I can take its natural log, and then out comes a real number. Yes.
Is target not the range?
Correct. Target is not the same as range. I'll talk about that more in just a minute. Yeah. Okay. Let's see here. So now this is going to seem a little silly, but I'm going to define three functions next here. All of these functions, for any given student, there's a student ID number, right? So I'm an easy little, it's a weird little rule of assignment. It's not a form. It doesn't have any algebra in it, right? But this is a rule of assignment because for every student, there's exactly one student ID number. Okay. Okay, but I'm defining these three functions, and they're all a little different technically. So this one, for every student, the student ID number is an integer. You might call this sort of the easiest way to define this function. But check this out. These two functions, they got the same domain, right? They're both taking in students. Let's say Duke students, right? They, however, differ in their targets. So they do not have the same target. And they also, of course, by the way, they have the same rule of assignment, right? These, both cases give student IDs. So nevertheless, these two functions, F and G, even though they're like, yeah, give me the student ID, they're different as functions because these trios are not identical trios. They disagree on what the target is. That makes them different. Neither one's right, neither one's wrong. They're just different trios, and therefore they are different as functions. Everybody see what I mean there? That's weird. And I can imagine you might thinking this is a pointless exercise. But things like this end up mattering annoying little ways. Everybody on board? So analogously, this function here also different. This has got a different domain than this function, right? These are different domains. I can restrict the function to only, this function I want to call H, I'm only defining it for students in this course. Makes it a different function. Okay. Okay, so somebody over there asked about what is range. So the range, which I like to call the image, I'll say another word about that in just a minute, but the range is the set of actual outputs. Okay, so the set of actual outputs, what actually comes out of this function, not necessarily the same as your target. So an easy example, right? You look at this function right here. is every real number somebody's student ID number? I'm pretty sure not. I don't think anybody has a student ID number that's pi, right? Wouldn't that be weird? So yeah, so there's a difference between what is allowed to come out of the function versus what actually comes out of the function, right? Those are different sets. So that's the difference. An algebraic example. You look at this function right here, f of x equals x squared. Easy function, right? Real number in, real number out. Well, the range, the image, the set of numbers that actually come out, not the same as the target. We're allowing real numbers to come, any real number, I don't know, I don't care, whatever, as long as it's a real number, that's cool, to come out of this function. What actually comes out? Just non-negatives. Everybody with me? Okay. Now, real quick, I want to talk about this word. I try to avoid this word myself. There is this problem that it means different things in different textbooks. In some textbooks, the word range is used as the same as target. Clearly not the same, right? They're different things. So some textbooks use the word range as synonymous with target, and other textbooks like ours use the word range as synonymous with image. So there is disagreement out there, as you know, in the community as to what that word actually means. And once that happens, once there's different people interpret the word in different ways, then it's no longer really a good way to communicate precise ideas. So good news, we have a perfectly good substitute, image. All right. So I just like to say image when talking about the actual outputs. Does that make sense to everybody? You're welcome to use range instead of image. I like to say image. All right. Okay, now some more lingo. Let's see, how are we doing on time? Oh, we started at 10:15. It's now 11:03, so we're short on time. No problem. So I want to talk about a little bit more lingo. I'll be super quick. I want to talk about, well, probably just get down to this. I want to talk about these words image and pre-image. So what comes out of the function is called the image for a given input value. The thing that went in that made that output is called a pre-image. And I think the lingo is pretty reasonable, right? Pre-image, because it's the thing that comes before the image, right? Do notice, though, that there is exactly one image output for any given input, but not vice versa, right? So you notice this word A here. There could be multiple pre-images. In fact, I'll just point to this picture here. Let's see here, for this output value, there's actually a couple of different pre-images. That's a pre-image, but also that is a pre-image. And so, you can have more than one pre-image. In fact, you can refer to the entire set, both of those together, as a set you could call the pre-image set. Or you can refer to the points individually as a pre-image. Okay. So that is going to arm us to next time define a bunch more words. And again, all of this is laying groundwork for everything that comes later in the course. Okay, good to see y'all finally in person. Don't forget homework due on Friday. It's again almost certainly going to be 1.7 will be the remaining section due, but let's wait until the end of today to make sure. Okay, see y'all later. Have a good one. Yeah, sure.